Welcome to the Deep Dive. Today we're tackling something I know is on the minds of many of you, seasoned leaders in manufacturing and engineering. You're absolute masters of industrial processes, systems engineering, adopting new tech. But what about when things get unpredictable? Like a production line hits a bottleneck you didn't see coming, or your design team is just stuck iterating. How do we find that lever to, well, break those cycles?
Precisely. And that liver increasingly looks like artificial intelligence, AI. And, it's different flavors.
Yeah.
Our goal today really is to give you a systems overview, kind of a shortcut, if you will, to understanding how these aren't just buzzwords. They're becoming practical tools. We want to demystify the core ideas, show how they actually connect to your world, and maybe most importantly, give you the right questions to ask for, strategic decisions.
Right. Cutting through the noise, the hype, and getting straight to how AI can genuinely drive efficiency, innovation, and, let's be honest, value in your operations. So let's just dive in. Why AI, and why now, specifically for manufacturing and engineering? Is this just another trend we can afford to sort of watch from the sidelines?
Well, think about the sheer amount of data that's just pouring out of our modern industrial environments. It's incredible. You've got sensor readings, production logs, engineering simulations, supply chain data. The volume, the speed, it's just immense. Frankly, human analysis alone, it just can't keep pace anymore, not effectively. AI really excels at processing these enormous data sets, finding those hidden patterns, forecasting trends, stuff that we just couldn't do before at this scale or speed. And that translates directly into smarter decisions, quicker reactions, right there on the factory floor or across the entire supply chain.
So it's not just faster number crunching. It's like unlocking a whole new level of insight because of the scale.
Yeah.
What does that actually feel like, practically speaking, day to day?
Exactly. It's like having this infinitely scalable, tireless analysis team working alongside your experts. And beyond just crunching data, AI can take over a lot of those repetitive, frankly, monotonous tasks. Think quality checks, monitoring alerts. That frees up your skilled workforce, your engineers, your technicians for the stuff that really requires human creativity and complex problem solving for innovation. So it's really not just about automation in the old sense. It's fundamentally about augmenting human intelligence, helping your best people do even better work.
That distinction, augmentation, not just automation, feels really key for this audience. Okay, but before we get into the how, let's clear up some terminology. We hear AI, machine learning, deep learning, generative AI. They often get thrown around almost interchangeably. Can you help us sort of lay out the hierarchy?
Absolutely. Think of it like a set of nested Russian dolls, or maybe for this group, like a complex system with its core subsystems. The biggest doll, the broadest field, that's artificial intelligence, AI. The main goal here is to get machines to solve problems that we normally associate with human intelligence. Things like learning, creating stuff, recognizing images, understanding language. It's about creating systems that can perceive, reason, learn, and act. So if your big picture vision is a truly smart, adaptive factory, AI is that overarching concept, that goal.
Okay, the grand vision. So what's the next doll inside?
Right inside AI, you've got machine learning, ML. This is a specific branch or maybe a set of techniques within AI. ML focuses on using data and algorithms to let computers learn without being explicitly programmed for every single task. You feed them data, they learn patterns, they make predictions or decisions, and they get better over time. So if AI is the blueprint for the intelligent factory, ML is like the sophisticated control system that learns directly from production data how to optimize things instead of needing engineers to manually write every single rule.
Okay, so ML is the learning engine within AI.
Yeah.
Got it. Then what's deep learning?
We go another layer deeper. Deep learning, DL, is a specific type of machine learning. It's heavily inspired by the structure and function of the human brain, using something called neural networks. These are essentially layers upon layers of computational nodes that process information in complex ways. They're really good at finding very intricate, abstract patterns in huge data sets. Think speech recognition or complex image analysis. So if ML is that smart control system, deep learning is like an incredibly advanced, multi-layered vision system on your assembly line. It could spot, say, subtle defects, maybe a tiny scratch or slight discoloration, without anyone ever explicitly programming, look for this specific scratch type. It learns what good looks like from thousands of examples.
That's a great analogy that really helps picture it. It gives that almost intuitive pattern recognition. Okay, so where does the latest buzzword, generative AI, fit in? It seems to be everywhere now. It really is. Generative AI, GenAI, is, well, it's a newer cutting-edge area, mostly driven by these very large, advanced deep learning models. You might hear them called foundation models. Now, Traditional AI and ML are often about classifying things. Is this a defect? Or predicting things. What will demand be next month? Generative AI, on the other hand, is focused on creating new original content. That
Yeah.
could be text, images, music, video, or even engineering designs or code. So if traditional ML helps optimize an existing design, generative AI is more like having a brilliant, incredibly fast design engineer who can brainstorm and generate entirely new concepts, new designs, new process flows, maybe based on just a set of requirements or constraints you give it.
Okay. It clears it up beautifully. So
Right.
AI, the big umbrella, ML, the learning process, DL, a powerful brain-like way to learn, and GenAI, the creative engine, using those deep learning models to make new stuff. That framework makes a lot of sense.
Exactly. And now that we have that framework, you're probably thinking, okay, interesting concepts, but how does this actually work in my world? What does it look like on the ground? Let's talk about some really concrete examples relevant to manufacturing and engineering environments.
Great. Yeah, I'm already starting to map this onto challenges I've seen or heard about.
Yeah.
Let's hear them.
Okay, a classic one, and probably one of the most mature applications, is predictive maintenance. Manufacturers are already collecting tons of sensor data from equipment, right? Pressure, temperature, vibration, flow rates. This is often time series data, meaning data points collected over time. ML models can analyze this stream of data to spot subtle patterns that often show up before a piece of equipment actually fails. This lets you schedule maintenance proactively before something breaks and causes expensive downtime. Think about an oil and gas company monitoring wells in real time to know exactly where to send maintenance crews, avoiding failures and maybe even environmental issues. This often uses techniques like anomaly detection, spotting data points that look weird or unusual compared to normal operation or regression to forecast the remaining useful life of a component.
That shift from reactive to proactive is huge. Huge cost savings, huge reliability improvements. Okay, what about quality? Always top of mind?
Absolutely. So next up, quality control and defect detection. This is where computer vision, often powered by deep learning, really shines. You can have cameras on assembly lines processing images or video feeds in real time. These systems can identify objects, classify different product variants, or detect tiny flaws, maybe a microscopic crack, a misaligned component on a circuit board. They can do this far more consistently, often faster, and sometimes more accurately than human inspection alone, especially for repetitive tasks. Now, this could be supervised learning, where you train the model by showing it lots of examples of good parts and bad parts, all carefully labeled. Or it could be unsupervised learning, where the model basically learns what normal looks like and flags anything that significantly deviates from that norm, even if it hasn't seen that specific defect before.
Wow, okay. That consistency is key. What about the design phase? You mentioned generative AI earlier.
Right. Let's talk about design optimization and generative design. This is where generative AI is starting to make a really big impact. Instead of human engineers having to painstakingly iterate through maybe dozens of design options, you can give a generative AI model a set of goals and constraints. Things like maximize structural integrity, minimize weight, use less than X amount of material, ensure airflow meets these parameters. The AI can then generate hundreds, even thousands of potential design solutions, sometimes exploring options a human might not have even considered. It can even generate code for simulations based on those designs. Think about designing complex mechanical parts, optimizing aerodynamics, or even finding novel material compositions. It dramatically speeds up the R&D cycle.
That sounds potentially transformative for innovation cycles, moving from weeks or months down to days or hours for initial concept exploration.
It really does have that potential. Let's also consider the broader picture. Supply chain forecasting and management. For any manufacturer, accurately predicting demand is absolutely critical. Get it wrong, and you either have costly excess inventory or you face stockouts and lost sales. ML models are very good at analyzing historical sales data, again, often time series data, plus maybe other factors like seasonality, promotions, even weather patterns, to predict future demand much more accurately than traditional methods. This helps optimize everything from raw material purchasing and production scheduling to warehouse inventory levels and logistics, like figuring out the best place to position delivery trucks. This is typically a regression problem, predicting a future number.
Getting that forecast right impacts everything down the line.
Everything. And one more, maybe slightly different angle, human-machine interfaces and even internal support. Think about your field technicians. They might need quick access to complex technical manuals, schematics, or troubleshooting guides out in the field. Natural language processing, NLP, which is another area of AI, can power chatbots or intelligent search systems. A technician could just ask a question in plain English, like, what's the torque spec for this bolt sequence? Or, show me the repair procedure for fault code 123, and get an immediate relevant answer. These systems can understand the intent behind the question, not just keywords. Some can even translate information between languages in real time. Think about the efficiency gains, reducing the time spent just hunting for information. We see this externally too, like those AI trip planners on travel sites. That's GenAI understanding natural language requests.
Those are all incredibly concrete examples. It
Yeah.
really feels like these technologies are moving beyond the lab and genuinely tackling long-standing challenges in efficiency, quality, and even innovation across the board.
They absolutely are. But, and this is important, like any powerful tool, AI needs to be approached strategically, thoughtfully. It's not magic. So let's shift gears a bit. How should you, as decision makers, as engineering leaders, actually think about adopting these technologies?
Right. What kinds of problems are they genuinely good at solving? And maybe more crucially, what are the pitfalls?
Yeah.
What should we be watching out for? Because let's face it, it's rarely a simple plug-and-play solution, is it?
Yeah. No, definitely not plug and play. You're right. So first, where does AI really excel? Massive data analysis. We touched on this. When you've got overwhelming amounts of data sensor readings, logs, design files that are just too complex or too fast for humans to analyze effectively, AI is a natural fit, finding those needles in the haystack. Repetitive, monotonous tasks. Things like visual inspection on an assembly line, monitoring sensor dashboards for anomalies. AI can do these tirelessly and consistently, freeing up your people for more engaging, higher value work. Pattern recognition and forecasting, identifying subtle, complex patterns that might indicate an impending equipment failure, potential fraud in transactions, or shifts in market demand. Creating new content. We talked about generative AI for design, but it can also be used for things like generating initial drafts of technical documentation, creating synthetic data for simulations, or even writing basic code snippets. Okay, so that's the potential. Now, the crucial part, what to watch out for. The challenges and limitations, first and foremost. Cost versus benefit. Training sophisticated AI models, especially deep learning and these large foundation models, requires significant computational power, which means cost. Cloud resources, specialized hardware, skilled personnel, it adds up. Before launching any AI project, you absolutely must clearly define the expected business value. What are you trying to achieve? Reduce waste by X%, increase throughput by Y, improve quality scores by Z. Quantify it. Then, realistically assess the costs. Make sure the potential return justifies the investment. Don't build a super complex deep learning model if a much simpler statistical method or even a well-designed rule-based system gets you 80% of the way there for a fraction of the cost. Especially consider the long life cycles of industrial assets integration cost is real.
That ROI calculation is critical, especially when you factor in integrating with potentially decades-old factory systems. Okay, what about understanding how these models make decisions? That black box thing comes up constantly.
It does, and it's a valid concern. This is the black box problem, or the challenge of interpretability. Highly complex models, especially deep neural networks, can function in ways that are very difficult for humans to fully grasp. You see the input, you see the output, but the exact why behind a specific decision can be opaque. Now, if you're in a highly regulated industry or dealing with safety-critical systems, think aerospace components, medical devices, maybe managing critical infrastructure, where you must be able to explain precisely why a decision was made for compliance or safety audits, then a less interpretable model might be unacceptable. In those cases, you might need to choose a simpler, more transparent model, perhaps sacrificing a bit of raw predictive power for the sake of understandability. Think decision trees or linear regression versus a complex neural network. However, it's worth distinguishing interpretability from explainability. Often for business purposes, you don't need to know the exact mathematical function inside the black box, but you do need to understand what factors drove a decision. Techniques are emerging to provide these kinds of explanations, even for complex models. So, explainability is often sufficient, but you need to assess that carefully.
That's a really important distinction, interpretability versus explainability. Okay, what else?
Another key difference, determinism versus probabilistic nature. Traditional engineering often relies on deterministic systems. Same input, same exact output every single time. Predictable, repeatable. Machine learning models, however, are generally probabilistic. They provide likelihoods, probabilities, confidence scores, not absolute certainties. They learn patterns from data, and there's often an element of randomness in their training or operation. Their predictions might change slightly, even with the same input, if retrained on new data. So if your application absolutely requires deterministic, unchanging output for a given input, A classic rule-based system or traditional algorithm might still be the better choice.
Right, that's a fundamental mindset shift for engineers used to deterministic outcomes.
It really is. And probably the biggest single factor for success or failure. Data quality is paramount. I can't stress this enough. AI models are entirely dependent on the data they are trained on. If your training data is incomplete, inaccurate, or biased, for example, if it only represents certain operating conditions, or if defect examples are rare or mislabeled, your model will inherit those flaws. The old saying, garbage in, garbage out, is amplified tenfold with AI. You'll encounter problems like overfitting, where the model learns the training data too well, including its noise, and then fail to generalize to new, unseen data. Or underfitting, where the model is too simple and hasn't learned the underlying patterns adequately. Both are often symptoms of data issues, not enough data, not diverse enough data, or poor quality data.
So it's like trying to build a precision machine tool on a shaky foundation. The data is the bedrock. And you mentioned generative AI specifically earlier. Any unique traps there?
Yes. Specifically with generative AI, you need to be acutely aware of hallucinations. These models, especially large language models, can sometimes generate outputs that sound completely plausible and authoritative, but are actually factually incorrect or entirely made up. They essentially hallucinate information, especially if prompted on topics outside their training data or asked to reason beyond their capabilities. For any critical application generating technical specs, safety procedures, even customer-facing information, any output from a generative AI must be rigorously fact-checked and validated by a human expert against reliable sources. Don't trust, verify. We've seen examples where generated content included fake legal citations or non-existent technical standards.
Oof, yeah, that could be disastrous. Verifying the output is non-negotiable then.
Absolutely. And finally, underpinning all of this, data privacy and security. When you train AI models, especially on proprietary operational data, sensitive customer information, or intellectual property like design files, you need extremely robust security measures. There's a risk that sensitive information embedded in the training data could inadvertently leak through the model's outputs in subtle ways. And once a model is trained on data, making it forget specific pieces of information is very, very difficult. So strong data governance, anonymization where possible, access controls, and secure infrastructure are absolutely essential. You have to protect your core assets and comply with privacy regulations.
Okay, that's a sobering but really necessary list of considerations.
Yeah.
Understanding the limitations the data needs, the probabilistic nature, the potential for errors, it's key. So given all that, how do we actually start evaluating opportunities? How do we move forward without getting paralyzed by the complexity?
That's the critical next step. It's about a structured approach. First, start with a clear business goal. Don't chase the shiny object. Don't say, we need an AI strategy. Ask, what specific, measurable business problem are we trying to solve? Is it reducing scrap rate on line 3, shortening design validation time for new components, improving forecast accuracy for key materials? Define the problem clearly, quantify the potential value, and get alignment from all the stakeholders early on. Then ask if AI is the right tool for that specific job.
Problem first, technology second. Makes sense.
Second, assess data availability and quality. We just talked about how critical data is. Do you actually have the data needed to train a model for your specific problem? Is it accessible? Is it clean enough? Is it representative? If you need supervised learning, is the data labeled correctly? E.g., images marked as defect or no defect. Data collection, cleaning, and labeling can be a significant project in itself. Can you establish repeatable processes for ongoing data gathering?
So a data readiness assessment is step one, really.
Absolutely. Third, evaluate solution approaches, focusing on cost benefit. Don't automatically assume you need to build a cutting-edge model from scratch. Your first stop should be, can we use a pre-trained AI service? Many cloud platforms offer services for common tasks like image recognition, text analysis, or forecasting, often accessible via simple APIs. These can be the fastest and most cost-effective way to get started if they fit your need. If a pre-built service isn't quite right, consider fine-tuning an existing foundation model. You take a large, powerful model that's already been trained on vast amounts of general data, and then you train it a bit more using your specific proprietary data. This leverages the initial massive training effort and adapts the model to your context. It's a very powerful and increasingly common approach. Training a model entirely from scratch is the most complex, time-consuming, and expensive option. Reserve this for truly unique problems where no existing models or approaches are suitable, and the potential payoff is very high.
That tiered approach service, fine-tune build, is really practical.
Fourth, consider explainability and compliance needs right from the start. If you know you'll need to explain model decisions for regulatory reasons or internal audits, factor that into your choice of model and approach. Don't wait until the end and realize your model is too opaque. And fifth, critically, plan for continuous monitoring and iteration. This is where ML OPS comes in. AI models aren't static, deploy once and forget systems. Their performance can degrade over time. Why? Because the real world changes. The data your model sees in production might start to look different from the data it was trained on. That's called data drift. Or the underlying relationships might change. Maybe a new type of defect starts appearing or customer behavior shifts. That's concept drift. You need robust systems in place, MLOps practices, to continuously monitor your model's performance in production, detect issues like drift or emerging bias, and have automated processes to trigger alerts, retraining, or model updates as needed. It's about applying good, solid systems engineering and DevOps principles to the entire life cycle of the machine learning model, ensuring it remains reliable, effective, and auditable over time.
MLOps. So bringing that engineering discipline to the AI lifecycle itself, that sounds absolutely crucial for long-term success in an industrial setting. Okay, this has been incredibly insightful, really practical. As we wrap up, what are the absolute key takeaways for our listeners, the things they should really focus on as engineering and manufacturing leaders looking to navigate this AI landscape?
Okay, if I had to boil it down, I'd say these are the most critical points. 1, start with the problem, not the technology. Always. Define a clear, measurable business challenge first. Then, evaluate if AI is the right tool and always consider the simplest viable solution first. 2, data is your foundation. Relentlessly focus on data quality, availability, governance, and security. Bad data will sink any AI project. Think about data preparation and labeling as essential investments, not afterthoughts. 3, embrace iteration and experimentation. AI development isn't linear. It's a cycle of training, testing, tuning, evaluating. Be prepared to experiment, learn, and adjust. Don't expect perfection on the first attempt. Leverage tools that make this iteration faster. 4, think augmentation, not just replacement. Look for opportunities where AI can enhance the capabilities of your human experts, taking over tedious tasks and freeing them up for higher value, creative, and complex problem solving. That's often where the biggest wins are. 5, prioritize responsible AI from day one. Embed considerations of fairness, transparency, or explainability, privacy, and security throughout the entire process. Understand the limitations, hallucinations, bias, and build in safeguards, human oversight, and robust testing. Proactive risk management is key. And 6, leverage existing capabilities first. Before you invest heavily in building custom models from scratch, thoroughly explore pre-trained AI services and foundation models. Fine-tuning an existing powerful model is often a much faster and more cost-effective path to value.
That's an excellent, actionable roadmap. Start with the problem, nail the data, iterate, augment your people, be responsible, and don't reinvent the wheel if you don't have to. This deep dive has really clarified how AI, ML, DL, and generative AI aren't just abstract concepts, but tools that can, and arguably should, be part of the strategic toolkit for manufacturing and engineering leaders today.
Absolutely. The future competitiveness of these industries, I believe, will significantly depend on how effectively organizations learn to adopt, integrate, and manage these intelligent systems. The opportunities for driving innovation, efficiency, and value are truly immense.
And the key, it seems, as it often is in engineering, comes down to asking the right questions, rigorously understanding the underlying principles and limitations, and maybe realizing that the most effective AI implementation often looks less like a futuristic robot takeover and more like your best engineers, your best processes, just getting smarter, faster, and more capable. Thank you so much for guiding us through this fascinating and really critical topic today.
It was my pleasure. Glad we could break it down.
And thank you all for joining us on this deep dive. We hope this exploration gives you some concrete ways to think differently about how AI can start transforming your world.